welcome everyone. Welcome to Christie's on this wet and rainy day. I want to also say about our partners here, Hyundai and Christie's Education. Thank you so much. We are pleased to work with you, and thank you. Technology is not to disrupt the art market. It's to supplement it, and it's to progress it. And by this conference, Christie's is committing to technology innovation, to growth, and digital strategy. Again, we are honored to partner with Hyundai, who is very committed to the arts community in a variety of ways. They have focused on LACMA's Art and Technology Lab. They have also focused on a series of videos with Bloomberg. They have also partnered with the Tate Modern in a series of 10-year commissions for its renowned Turbine Hall. It also has focused on Hyundai Tate Research Center, transnational, which focuses on expanding the collections of the Tate outside of North America and Western Europe. Again, it's an honor to be partnered with them, an esteemed organization. And we also hope that you enjoy the exhibitions that we have jointly curated together. I want to thank everyone for this particular conference and for the impressive group of speakers, curators, and artists who will be contributing today. I look forward to learning with all of you. It is now my great pleasure to introduce the Chief Marketing Officer and Executive Vice President of Hyundai, Mr. Wong Hong Cho.
Good morning. Welcome, everyone. Thank you for being here today. My name is Wong Hong Cho. As introduced by Jet, I'm Chief Marketing Officer of Hyundai Motor Company. It feels like a perfect time for Hyundai Motor to present this Art and Tech Summit on artificial intelligence in collaboration with Christie's. It feels like a really perfect time. And as a leading mobility and technology company, it is our own responsibility to question and reflect upon what it really means to human being, especially for the purpose of the progress of humanity. In the first industrial revolution, we at Hyundai think that people need to be connected to each other through emotional values. Fun, relaxation, immersive experience, and togetherness will be key values which will increase the quality of our time. Every era is a tipping point in human development. As technology is becoming deeply embedded within our society in new ways every day, our vision for technology is not just practical, but also cultural. As today's summit will demonstrate in detail. We have always been seeking for clues on how technology could be transformed into meaningful human experience through our vast area of activities. At this summit, we hope to provoke respectful debates on and around a more inclusive and sustainable future. I also like to invite you to the Future Landscape, an exhibition presented along with this summit. You can find ways, and also works by international artists, including Quayola, Universal Everything, Wow, and two Korean artists, Shin Seung-baek and Kim Yong-hun, and also Mike Taika. By walking through the exhibition, we can feel and see how art and technology can positively influence each other and change our future landscape. It shows where the future is heading and what questions we should ask ourselves. Christie's is a name which we associate with global innovation in many global platforms. In that sense, we are all excited for this collaboration. And I'd like to thank Christie's. And last but not least, I'd like to thank the panelists and also all the distinguished audience. Thank you so much.
Thank you for joining us for our second Art and Tech Summit. Art and technology are inextricably linked. As we dive deeper into the digital era, more advanced tools are becoming available for us to simplify and expand our complex market. We can attract new clients and help more people understand how to enjoy art. We will incorporate more transparency into our businesses, create new vocabularies, and help close the gap between art and technology for the benefit of all. Now, it's been a busy year since our last summit. Christie's collaborated with Artery and registered the Ebsworth collection on a blockchain platform. The Whitney offered a blockchain-based donor program. The Met collaborated with MIT and Microsoft on an AI project. Philips partnered with a digital art company. The MoMA and other institutions around the world exhibited art and tech shows. The fashion conglomerate LVMH registered 60 brands on a blockchain, and New York hosted its first digital art fair. Clearly, there is market hunger for this dialogue. Last year, we explored blockchain. Our topic this year is artificial intelligence. How can predictive analytics, data, and neural networks impact our industry's tools? How will they affect artistic creation and consumption? How are other industries using it in their creative and corporate practices? Our goal for the summit is to create a forum for thought leaders, innovators, students, artists, clients, scientists, anyone who is thinking critically about the future of our industry. We want to cultivate new ideas, challenge current ones, and inspire. And our first step toward that goal is education, and that's why we're here today. We want to merge audiences and expertise. There are too many parallel conversations happening in different realms of the creative world for different audiences. Let's share our knowledge. I am so excited about today's agenda and our curated exhibition downstairs, none of which could have happened without the generous support of Hyundai and their incredibly hardworking team. So enjoy it, get inspired, and share your thoughts. After all, we are developing the new digital art world together. Thank you.
Good morning, everyone. And thank you for being here, and thank you to Christie's for having me here. I have been instructed to explain all of AI in 15 or 20 minutes. And we recently published a text study of AI research papers published in the last 25 years. There are something like 17,000 of them. So trying to summarize AI is trying to summarize all of European history and explain how it led to Brexit. I'm going to do my best nonetheless. You'll have seen some of the exhibition downstairs. You may have noticed that a lot of the AI-generated art looks somehow spooky. And I will attempt in what follows to give a couple of hints as to why it looks spooky. But I thought I would start by giving a quick breakdown of some of the main terms in AI that you might encounter during the day. So this is a flowchart that one of my colleagues, Karen Howe, made. When we talk about AI today, it's a big field that's actually been around for more than 60 years, but when we talk about AI today, we generally mean machine learning. And machine learning essentially means trawling vast amounts of data looking for patterns. This is to distinguish it from what was previously the vogue up until the mid-80s or so was expert systems, which are essentially huge databases of knowledge collected from human experts. And the problem with expert systems is you need a lot of human experts and a lot of knowledge to create that database that a machine can then use. So machine learning simply gives the machine a bunch of data and lets the machine itself draw inferences and learn patterns by studying the data without being told things about the world. But there are various subsets of machine learning. So one example of machine learning is what's called supervised learning. If you tell something, an algorithm, what to look for instance, you say, here are 1 million pictures, These are pictures of cats. Those are not pictures of cats. I'm going to be talking about cats quite a lot, by the way. Then it can learn to identify cats, but it can't, for instance, learn to identify rabbits because you haven't told it what is or is not a rabbit. But it can get very good at spotting cats. So that is supervised learning. If, on the other hand, you don't tell it what exactly to look for, then there are a couple of other variants. One is called reinforcement learning. Reinforcement learning is the carrot and stick approach. You give an algorithm a bunch of data and you give it a goal. Reach this goal, and by trial and error it learns to attain the goal. And this is the kind of technique that is used to teach computers to play chess or Go, for instance. The next main sub-branch here is called unsupervised learning. And unsupervised learning means you essentially give it no parameters at all. You just give it the data, and then it goes and searches for patterns. And so this is the kind of approach you might use if, for instance, you want to you might be Cambridge Analytica and you want to analyze all of the voter data and look for patterns and identify patterns that nobody knew existed. Now, on top of all of this, there is a question about how powerful the technique is. So you may hear the term deep learning. Deep learning means it uses deep neural networks. A neural network is essentially a kind of machine model that attempts to approximate something like the way the human brain works. It doesn't really approximate it at all, but it's a technique. And if that network has multiple layers to it, then it is called a deep neural network. And so the most powerful machine learning algorithms are ones that use deep learning. This is a technique that's been around about 7 years. So it can be called deep learning, deep supervised learning, deep reinforcement learning. If not, it's just machine learning. So here's one example of reinforcement learning. This little robot is called the Minotaur, and it was trained to walk. And it wasn't given any information about what walking is. All it was given was a goal, move forward. It was rewarded if it achieved higher velocity, and it was punished if it fell over. So to begin with, as you see, it sort of just moves its arms and it moves its legs. It doesn't really know what walking is, but over time, it gets better and better at moving forward. And over the course of about 2 hours, an hour and a half, it learns to walk. But notice that it walks in a funny way. It doesn't walk exactly the way an animal does. It's just using its legs in a way that it has learned to move forward. And once it does that, it will just keep on going. So that quality of machine learning algorithms, that they learn to do a thing, but they don't necessarily learn to do it the way you expect them to do it, is part of the reason why AI art sometimes looks uncanny and spooky. It's imitating what we've taught it to do, but not in quite the way that we think it should. Here is an example of something that is called of unsupervised learning. This an algorithm called GP2. GP2 was originally trained on databases of text, and you can give it a starting point, a paragraph from Lord of the Rings, or the opening of a news story, for instance, and it will generate really quite plausible fake text from that. So it will spin you a chapter of Lord of the Rings that you would actually have to read fairly closely to realize that it wasn't the real thing. It can also generate music. So this was trained on the Bach Ode, and this is music that it generated that is in the style of Bach. So I don't know if there are any Bach experts in the room who can tell me just how likely it sounds. Anyway, that gives you a sense. Another technique that you may well come across, because it comes up a lot in the art world, is called generative adversarial networks, or GANs. And the idea here is that you pit two machine learning algorithms against one another. One of them is trying to detect fakes, and the other one is trying to generate fakes. And so they're essentially trying to outwit each other. And the way that this works can be imagined as a little bit of maybe a kind of a conversation. This is a cat. Nope. Well, maybe this is a cat. Nope. And as the generator gets better and better, it starts to create images that are a little closer to cat-likeness, until it starts to create some really quite weird ones that are not quite there. But finally, it can generate something that is so close to a cat that another machine, or even a human, cannot tell that it is different. So GANs have been used to generate artworks. They can be used, for instance, to generate fake images that can be used as training data for other AIs. So a good example of that is for self-driving cars. You can train a self-driving car by driving it through landscapes, or you can use a GAN to take real pictures of landscapes and generate fake landscapes, or take real landscapes and overlay them with snow, for instance. And then you can train a virtual version of that self-driving car in simulation, and thereby drive many, many more virtual miles than you have time to drive real ones in the real world, and that can make the training much more effective. GANs are also used to generate what are called deepfakes. So these two sets of images are from a company called NVIDIA, which makes AI chips. And the top set were made in April of last year, and these are all fake faces. None of these people exist. And you can see that a couple of the faces look, again, kind of uncanny, kind of spooky. Something's a little bit off about them. But just a few months later, the algorithm had already got significantly better, and it was already much harder to spot which faces were unreal. So there is already worry about deepfakes being used in political campaigns to make politicians say things that they didn't say. But on the flip side, the good news is that this kind of software can be used for spotting fake images. This is not actually a deep fake, it's just a picture where the guy's head was swapped around. But an AI algorithm can learn to identify what is wrong with a picture and flag it as a fake. Now, one of the worries, of course, one of the ethical worries about the uses of AI is that it can be very effective for surveillance. If you can collect data on huge numbers of people and then analyze that data, you can spot behavior patterns. So recently there was a study that showed that you could use an AI to, it was analysis done on Hollywood movies, and the researcher essentially got the AI to pick out all of the scenes in which people were kissing. So imagine that you have an AI like that trained on city surveillance camera data. It can catch all the images of people kissing or images of people doing other things. Could be used for quite Orwellian purposes. Another of the problems with this kind of use of AI for face recognition is that it's only as good as the data it's trained on. And there's been a problem of AI bias, particularly resulting from the fact that most AIs hitherto have been trained on data sets that tend to correspond to white people, and especially white men. And so Amazon has a publicly available AI face recognition algorithm called Recognition. It was tested on members of Congress, and it was used to match members of Congress to databases of convicted offenders. And it found 28 false matches, 28 Congress members that it thought it identified as convicted criminals. But more worryingly, a disproportionate number of those false matches were people of color in Congress. Another of the worries about AI is that it concentrates a huge amount of data. To feed these machine learning algorithms, you need vast quantities of data. And so that means that people end up with control of that data. This is obviously one of the big worries about Facebook consolidating its user data across all of the different services it provides. So one of the techniques that is being used to counter that worry is being applied in healthcare. It's called federated learning. So in traditional machine learning, you take all of the data you can, you feed it to a computer, and you let it do its stuff. Federated learning is a technique that allows, for instance, healthcare providers like hospitals to keep their databases separate, do machine learning on their own data but nobody else's, and then the federated learning system manages to take the results from all of those different machine learning algorithms that are shared by the hospitals and extract data, patterns from it or do analysis on it without actually having access to the original sets of data. So it's it creates a barrier, if you like, between the data and the analysis. And so this is a technique that is still relatively in its infancy, but it offers promise for allowing us to do AI analysis on very large data sets without actually compromising people's privacy quite so much. This slide is a little bit random looking, but I'll explain it. Another problem that AI has is that it takes a huge amount of energy. So as you may know, blockchain, for instance, requires an awful lot of energy generation to mine cryptocurrencies. Training AI algorithms, it turns out, requires an awful lot of energy generation as well. that creates a climate change problem. Part of the reason that it's so difficult is that you have to, when you train a machine learning model, you're actually kind of throwing the dice, playing the lottery. For every for every machine learning model you generate, for every 10 learning models you generate, only one of them necessarily will be trainable. So you're effectively creating AI algorithms and then throwing a lot of them away. So some new techniques are finding ways to predict which algorithms will be effective and thereby reduce the energy use that they have. Now, there's another side to AI, which is that AI isn't always AI. A book by someone called, a book called Ghost Work by Mary Gray and Sadat Suri is about the effects of all of the services that rely on human beings to supplement their AI. So, for instance, when you use a face recognition system, or when you use a voice assistant, that voice assistant has not only been trained by human beings, but sometimes human beings are called in the background to fill in when it's not doing its job properly.
El Cocotero, how may I help you?
Hi, I'm the Google Assistant calling to make a reservation for a client. This automated call will be recorded. Can I book a table for Tuesday the 12th?
Okay, cool. And how big is the party?
It's for 2 people.
Great.
So that is Google's Duplex, which is now available across most of the US. And it makes calls on your behalf to schedule things. But it revealed that in some cases, those calls are actually a human being intervening because the AI wasn't quite good enough for the task. I'm going to close by talking a little bit about an area that has some relation to the art world, which is the fashion industry. So I wanted to discuss some of the applications of AI in an industry. Fashion is a good example. This is an app called Style Match by the fashion company ASOS. And what it does is it allows you to take a picture of something with your phone and then find products on ASOS's website that match it in style or in color. Another similar app called IntelliStyle will learn your preferences and trawl the web for objects that might match your tastes. And this is an example of an experiment that Tommy Hilfiger did with IBM, the Fashion Institute of Technology. And what they did was effectively scan hundreds of thousands of images of Hilfiger clothing, feed that to an algorithm, and then use that algorithm to allow fashion students to design new clothes that had the Hilfiger DNA in them. And this was an example of a way that you could use, as a retailer, for instance, use AI to react fast to trends in the market and come out with new clothing. So these are just some of the examples of the ways that AI can transform all of these industries. That was my summary. I did even less time than I thought I would need. And thank you very much. I hope you enjoy the rest of the conference.
I'm going to talk a little bit about my background because I think it helps understand some of my stranger ideas and my projects, and then talk about something I call the art data crisis. We'll talk a little bit about machine learning, and then I'm going to get into some predictions, or at least where I think we might be able to find some value in the art market. So I was born an artist in a family of engineers about an hour outside of Boston. My parents started their family really young, so we didn't have a lot of money growing up, but I pretty much lived in the art museum with my dad. So it was our clubhouse and our classroom, and I remember that he was always fascinated by the Egyptian statues. It doesn't show in this slide, but they always had this like left foot forward pose that like was consistent throughout hundreds of years. And I kind of found that boring when I was younger, but I was fascinated by how quickly things changed just in the last 100 years. So the 20th Century Gallery used to be near the exit, so we had to go through there just to leave, and he was not a fan. And I would always like freeze in my tracks. That was always the work that I found most interesting. And I decided at a pretty young age that I wanted to be a painter, and that's all I wanted to do. So I spent a lot of time looking at art history and artworks, and I wasn't a great student in high school, but luckily I built up a portfolio that got me into college. Can everybody hear me okay? Yeah, great. And then college was was paradise for me. So I got to focus in on art history and spend a lot of time in the studio making paintings. And then it wasn't until I graduated that I realized that art was sort of like a status symbol, and there's like a market associated with art and such a thing as an art star. And I thought, oh, cool, maybe I can be an art star. And I learned pretty quickly I cannot be an art star. So I surrendered and kind of went to the family industry, which is tech. So I spent the last 20 years working mostly at startups in the Boston area. Most recently, a startup called Tamer. It's a machine learning startup that was started by Dr. Michael Stonebreaker, who won the Turing Award a couple of years ago. So it's like the Nobel Prize for computing, super bright guy. And that's where I started learning about machine learning. And on my commute into Tamer in Cambridge, I had like an hour-and-a-half long commute both directions, so I listened to a lot of audiobooks. I was listening to this book, Provenance, 2 or 3 years ago, and what blew my mind is that not only were paintings being forged, but people were forging the actual provenance documentation, which for someone like me, where art history is like a religion for me, it was like an assault on my religion that people could do that. And I dug in a bit deeper, and I know we can all debate until the cows come home whether this number is accurate or not. I try to shoot for something that's a little bit on the conservative side. The nature of the statistic makes it impossible for anyone to really know, right? But what I had read is that 15 to 20% of art is either forged or misattributed. And that kind of blew my mind. So I did some basic math, and if you look, 400 artists roughly worth forging. Each one makes roughly 1,000 paintings. That's a total of 400,000 works. If we assume there's 100 forgers out there, and each one makes roughly 1,000 paintings, that's a total of 100,000 works. So I can name 20 forgers off the top of my head. I don't think that number is too crazy. So we kind of talked about that already. And so essentially what I did is I reached out to all the Ivy League libraries and the Smithsonian Institution and the Getty Research Institute, and I said, look, where's the database that has the complete works from all the best known artists? Like, if we had this database, we wouldn't have forgery, right? And they all said, sadly, no such database exists. And this blew my mind because we have multiple databases online of the complete Pez dispensers, right? And like a dozen like databases about like Beanie Babies, like the complete amount of Beanie Babies, right? So we know more about Beanie Babies and Pez dispensers than we do about our most important cultural treasures, our art. Which is weird because we have all these signals socially, right, that we care about art. So every year, every major college has an art history department, and we graduate all these art historians. We have these buildings that are temperature controlled, and we man them with security so you don't touch the paintings. We have people spending up to hundreds of millions of dollars on single paintings. But when you go to Google, which is where everyone goes to get their information today, and you ask, how many paintings did Mark Rothko paint? It comes back with at least 4, right? So forget analytics, like let's just do counting first, right? The basic stuff. So I was so worked up about this that my wife got tired of hearing it, and she was like, try to solve it, try to solve the problem. I'm like, I'm gonna try to solve the world's like art data problem. And I thought, well, maybe I can at least loosen the lid. So coming from a family of engineers, I reached out to my older brother, and he helped me build this contraption so that I could scan catalog raisonnés and pull the metadata out, the factual information, which my understanding is you can't copyright. No one sued me yet, so thank you. And so there's 2 cameras that shoot down with a little platen that you lift up and down, and I've got this bag on the right side that you scientifically weigh down with spaghetti sauce to make sure that everything's balanced. And then after 2 or 3 years of this and thousands of dollars and hundreds of hours, it like dawned on me one day that I had like no end game. And if I got hit by a bus, like no one would know where the data was or like why I was doing this. So I made a blog called artgnome.com where I talk about the intersection of art and technology. And in the early days, that was largely about this database and things that I was discovering that other people probably hadn't known yet. So not just how many paintings each artist had made, so this was a comparison article, but things like what % are portrait aspect ratio versus landscape aspect ratio, and then showing productivity over time. So I won't dive deeply into any of these charts, but this is Van Gogh and Pollock showing their volume of work. So this relative size of surface area painted. So even though Van Gogh painted more paintings than Pollock painted more surface area. Looking at things like their complete body of work by height and width. I got my hands on some auction data and was interested in this cost per square centimeter thing, which everyone scoffs at because it's kind of like hamburger per pound. They're like, you can't talk about art that way. But what's interesting is if you combine that, once you know the height and width of an artist's complete works, you can start to estimate what the total market cap might be and compare one artist to another and say like, maybe they're overvalued, maybe they're undervalued. So there's this global view that you can start to create. It also changed the way I appreciated art. So the tallest Jackson Pollock painting I figured out is at the Harvard Art Museum, just like a couple blocks from my work. So I went there, and it was sort of symbolic because Harvard's like considered like this amazing academic institution, but there's no way that they would have known that they had the tallest Jackson Pollock painting because all that information is stored in print, right? And it's really hard to do analysis on print. And it turns out the smallest Pollock painting is actually in Connecticut, just down the street. So I might visit that one on the way home. And it got me thinking about projects differently too. So I had heard that Van Gogh, his color palette had turned from brown to yellow because of the Impressionists when he was in Paris, or because he had digitalis poisoning that gave him yellow vision. But I worked with Art Gnome data scientist Kyle Waters, and we took every single painting from every location that Van Gogh lived in, and we averaged out the pixels by location, and then we got the weather patterns for each of those locations. And if you look, you can see as the locations go chronologically, they get lighter. And this slide shows you that it's actually after Paris, right, that we see the yellow and the brightening of the palette. And it's before he was being treated with, I think it was foxglove that maybe had the digitalis in it. But more importantly, there's this giant spike in sunshine, right? So why did Van Gogh's color palette change? Because he had more exposure to sun and he was painting what he saw. So this was a fun article. It's starting to march up the search results on Google. Quickly on this one, quantifying abstraction. So I think we all know that Mondrian's painting style kind of got more and more abstract over time. So one of the cool things that happens when you have a lot of data is smart people reach out and want to talk to you. So I worked with Alexander Koch to try to figure out if we could get a single number to try to predict how abstract a painting was. So this was his algorithm. And we went through all of Mondrian's work. And what becomes problematic is that a lot of people, as they get more abstract, say like Pollock, they actually get more complex. And we were using essentially complexity as a surrogate. So I was lucky. 538, the great data journalism site, did this big article on me and came into my house. That's where those earlier pictures were from. It kind of put me on the map and made me realize that I'm not just one nerd who wants to do this. There are a lot of nerds that want to do this stuff. So you're probably wondering, what does data have to do with machine learning? We're all here for machine learning and AI. That's what everyone's excited about. Well, actually, it has everything to do with machine learning. So quick definition. I don't really have to give this because Gideon did such a great job. But artificial intelligence is the science of teaching machines to think like humans. It's a simplified definition, but I think it helps. And where people that I talk to get stuck is, what's the difference between machine learning and artificial intelligence? So machine learning is models built on lots of training data used to make predictions when new data is added. So a couple of quick machine learning projects that I've worked on. Back in 2017, I built something called the Munch Visual Search Engine with my younger brother. So we took a subset of Munch's 1,800 or so paintings, and we trained a model to be able to identify if you were indoors or outdoors, if there were people in the picture, and then applied that model to the remaining paintings. That's a laughably small training data set, but we were able to build on an existing model that was trained on photos, and it actually did pretty well. But where it gets caught up are actually some of the same areas where humans get caught up. So how many people here think this guy is like wearing a hat? Anybody? I thought he was wearing a hat. But it turns out I went and saw a photograph, and the guy just has permanent hat head, right? So the models just get like caught up in the same spots we get caught up. So another project I did again with Kyle Waters, when the Ebsworth collection came to auction here at Christie's end of last year, he selected this random forest model. I won't get into it because it's kind of complicated, but essentially it does better with smaller data sets. And there's this problem with art and data sets. This is a correlation matrix to show what our model, which features it thought correlated strongest to hammer price. So interestingly, length was one of the big ones. And we looked at 4 paintings, Georgia O'Keeffe, an Edward Hopper, John Marin, and Arthur Dove. And it did pretty good. So this is a small sample size, right? But our mean error was about half that of Christie's predictions. It helped us so Christie's does a great job. I know I'm in Christie's. But it helped us that they kind of whiffed on the Marin painting by quite a bit. I think if you took that one away, we're probably pretty similar. So the model has a lot of potential. We've had a few people reach out that want to help us build it. But it comes back to the same problem of not having enough data. So our data is very small. I think ArtNet maybe has the largest database at like 10 million, which sounds big, but like Facebook, 300 million photos per day get uploaded. So these machine learning models are like super data thirsty. And then there's this other problem that machine learning perpetuates bias. So when I look for value, I try to actually find bias, and I think that that's where you find the value. So I like things like Moneyball. I think a lot of people here probably have seen the movie or read the book. And in Moneyball, so there's this, the hero of Moneyball, or one of them, is Kevin Youkilis, who Michael Lewis calls a fat third baseman who couldn't run, throw, or field. So Youkilis ended up going for, he ended up going to the Red Sox. Billy Beane, who was the manager of the Oakland A's, didn't get him. And he ended up helping us break like an 86-year World Series drought, right? So the idea is maybe he wasn't the best player on the team, but you have to get a bunch of people that are undervalued and find them. I think we all know when you see somebody really tall, the first question you ask is like, oh, do you play basketball, right? So there's a long list of really tall basketball players who were pretty crummy. And this guy, who's about my height, has been the MVP like 3 of the last 4 years or something like that, right? And you think tall people closer to the rim, it makes sense, right? But he does all his damage out in the three-point line as far away from the rim as possible, right? And this chart actually shows it's not just Steph Curry. This is like 20 years or so of how many three-point attempts the MVP in the NBA has taken. And you can see we're just getting further and further from the rim. So how can we apply this knowledge to finding value in the art world? Well, one really obvious bias is that art by women sells for 47.6% less than art by men. A lot of people scoff at this statistic too and say there's a few men that skew this and it's probably closer to 25. And I'm like, that still seems like a pretty good deal. So why? Why is that the case? And I think part of it is that art by women makes up just 3 to 5% of major permanent collections in the US and Europe. And I think that's going to change. So if we think about the Hilma Alfklint exhibit, I don't think 99% of people had no idea who she was 2 or 3 years ago. And she had this show that brought in 600,000 visitors. It's the most visited exhibition in the 60-year history of the Guggenheim. They broke the catalog sales record, 34% spike in membership and sales, and it's now one of the 10 most popular modern shows. So why does that matter if you're a collector? Well, one of the best studies on machine learning and art was done by my close friend Ahmed Hosni 4 or 5 years ago. And really one of the big things that came out in his analysis is that auctions of valuable pieces tend to coincide with successful exhibitions. So when people look at the Hilma Alfklint exhibit and they realize that it's breaking attendance records and we have more shows with women, you're going to see attendance drive up and more museum shows, which should drive up the value of the work as well. And all of that analysis could also be applied to artists of color. So currently 85% of artists in major museums are white. And less than 3% of acquisitions in the last decade have been work by African Americans. So I think as they get more exposure, and we're seeing a little bit of it, and people actually ask me, they're like, yeah, but isn't it like overheated now, the market? I'm like, no, it should be complete, should be like parity, right? So, I mean, I've spent half my life in art classes, and I've never seen someone's skin color or gender make them good or bad at art. There's a lot of things that'll make you good or bad at art, but it's not that. So one maybe less obvious area where I think there's some bias is actually tech and art. It's ironic to say that here because we're at Christie's. So the way I look at it is like computers and computing are pretty much the biggest thing that separate us from all the previous generations. And to me, generative art or software art is the history of computing made visible, right? So this is our art. This is like our generation's art, right? These are, in my opinion, the most important artists of our time. So this slide is for a show that I co-curated with George Bach, who's in the front row here, where we really tried to tie together this entire history of generative art all the way up to AI art. So one of the coolest things at the opening, Herbert W. Franca, who's 92, George, is that right? But 92 years old, came to the show and to support us and for us to support him. And so often in art history, like the great artists don't get recognition while they're alive, and we have a chance to do that with generative art, right? But there's a lot of value to be found in generative art. So this is a work by Freder Nack. It's a tribute to Paul Klee from the early 1960s. John Maeda, who a lot of folks maybe know as the former president of Rhode Island School of Design or as the head of the MIT Media Lab, but he was also a super important, talented generative artist from the 90s. One of my favorite generative artists that when I was a bratty painting student who thought digital work was all stupid, Jared Tarbell's work actually sort of converted me. This is amazing work by Manolo, who I consider to be the most talented generative artist working today. Uh-oh, I got runaway slides. That previous slide was by Harold Cohen. Let me see if I can get the reverse button here. Boom, awesome. So we think maybe this whole AI art thing is like so big in the last year, and a lot of people think that it's like a brand new thing. Harold Cohen was doing this in the 70s, 80s, 90s, and 2000s, right? So there's this great history that actually ties it all together. And of course, we had work by the contemporary AI artists like Anna Ridler, Mario Klingemann, Helena Sarin, David Young. And my favorite AI artist, Robbie Barrett, who's going to be on stage with me in conversation later today. Woo! So yeah, I think my summary slide got lost in there somewhere, but off the top of my head, I think hopefully what people take away from this is that we need more data. If we want to do cool stuff with machine learning, we need more data. If we want to do basic analysis, we need more data. If we want to fight the forgery, we need more data. And then the other thing that I would say is let's be careful with machine learning in terms of propelling the strong bias towards people that look like me in art that we have today. And try to find other ways to augment that. I think it's a chance to do well and do good by investing in people that have sort of been underrepresented. So yeah, I think that's it. And if you want to learn more, you can go to artgnome.com or email me at jason@artgnome.com. Thank you.
My name is Daniel Dubrovkin. I go by DB. I'm a former CTO of Artsy. I'm sure you all know. I have the pleasure of hosting Dr. Ahmed El-Gamal here. Nice to have you here.
Thank you
for being here. We want to talk about AI tools, and I love seeing slides about AI and technology in general. I think in the intro, slide 5 had two cameras facing in different directions. And that's a great image. I remember walking in stores as a kid and seeing cameras around. They had, at some point, I saw what was happening in the back room. There was a lonely VCR that would record these images. And then nobody would probably look at those videos except for when kids stole something from the bodega or something like that. But today, there is no more VCR. It's a computer. And sometimes it's not even a computer. These images get sent to the cloud where they get analyzed by hundreds of thousands of computers and can do some really impressive analysis of those images at a very different rate. So we can't take those cameras for granted as they were before. So Ahmed, what is the real state of image recognition that we have in that software today that analyzes these images?
Great. It's great that you started by talking about surveillance. I have been in the field of computer vision for almost 25 years, and one of the first things I did as an intern in my graduate school back in 1996 was I was an intern at Philips Research Lab in upstate New York when they gave me a box of a surveillance camera, that band-tilt zoom camera that was first released to the market. And my job was to build a system to recognize people and cars and events happening in that. So a lot of things has happened since then. So now, can we see the slides? Yes. So now cameras are everywhere. So surveillance cameras are everywhere. Cameras in our pockets, in our hands, in cell phones, watching us from satellite. Even inside our bodies, you can have a pill that go into your body. So a lot of development have been going on in computer vision in the last 50 years. Now it's driven by all this market. And nowadays, computer vision is so sophisticated. It can recognize objects like cars, people, cats, dogs, and also recognize the geometry of a scene to tell where is the street, so you can navigate and drive a robot or autonomous car, and even can give you a caption for an image like that. And it's also behind all the new wave of AI art by having computer vision techniques synthesize images that are used now to make art.
So that's interesting. So the technology today can take every frame of every camera that's out there and recognize cars and this kind of objects. How can we use this in art at all?
Yes. So art is way more sophisticated than recognizing object. Of course, if you look at art like that, we don't just look for that there is a man, there is a woman, there is a fruit, there is a tree. art has several layers of understanding that happens when we humans interact with art. Not only understanding, art affects us at emotional level, make us happy, make us sad, make us think. Machines are way beyond in that. I'm pointing you to here to a couple of blogs by Shelley Bernstein from the Barnes from 2 years ago, when they had a project to use AI and vision to allow their users to navigate their collection based on formal elements, the same way the Barnes imagined his museum in Philadelphia. And it's an amazing blog because basically I'm having a quote here. She said the first part of this project we used 6 services: Microsoft, Azure, IBM Watson, Google, AWS Recognition, TensorFlow, Carify, to look at the painting in our collection to tell us what's in them, trying to use vision and AI to do that. And this is what they found out. So a Renoir like that, the AI tell a boy holding a teddy bear, Modigliani, another teddy bear. So the conclusion was, again, I'm going to read here that quote. What the computer saw were lots and lots of stuffed animal in the Barnes collection. I can't count how many times the tag stuffed has shown up in the result, and a teddy bear seemed to make it into the image caption more often than you would think. Anyway, 3 years earlier, back in 2014, at the Art and AI Lab. Actually, I founded the Art and AI Lab about 7 years ago exactly to solve this problem, that AI cannot understand art, and by understanding art, we can actually advance AI. That was my theory. 5 years ago, we showed the discovery, basically, where we showed that if we learn the machine how to know, how to understand art a little bit, it can make discoveries. Like here, one of the art in the left by French artist Basile, the artist studio, and the one on the right by Norman Rockwell. There are 70 years apart, and no art historian have ever saw them side by side. But the machine find there is a potential influence here. And when you look at them carefully, you realize that, yes, there is. There are 3 people in each of them. There are oven in the right side of each of them. There is a chair in the left side of each of them. There's a big window in the background in each of them. There's a stairs going up in the left, parallel to the frame, tilted in the right. So there are great compositional similarity between them. Was there an influence between them? Is Norman Rockwell was influenced by that? I'm not an art historian, I cannot tell. But as a computer scientist and an AI person, I reached the point that yes, AI can really look at art and can tell us things that we do not know.
But it seems purely coincidental, these sort of look alike and have all these objects. Are you really saying that the machine is understanding the art that it's looking at?
To a certain level, yes, at the formal element level. And let me talk about this figure. This is basically a year ago results. Again, where we trained the machine to understand styles of art in the last 500 years of art history, Western art history. And the only information we give the machine is what the style of each image is. It's a Renaissance or Baroque or Impressionist beside the image. That's the only information we give the machine. And we look at how the machine actually would classify style. Is it related to art historian notion of style at all? And many interesting discoveries have made here. One thing is, for example, is that we can capture most of the information in the visual form of art history using 2 factors, which are shown here. And moreover, the machine puts art history in a correct chronological order, which you see here in these slides. In the bottom, you can see Renaissance, and then you can see the movement to Baroque and moving to 18th century art to realism, and all the way up to Impressionism, and then going to Cézanne, and going to modern art, Picasso and abstract, and then closing the loop and coming to pop art, which close back to Renaissance. Remember that we never give the machine any information about time. We never told it when the art was made, or Renaissance happened before Baroque, for example, or Baroque happened before Impressionism. The machine figured out by itself that art history evolved in a very smooth way and discovered this smooth way by itself, which actually resonates with even what art historians have hypothesized before. Wolverine, the father of art history, has a quote that art history evolved like a rock going downhill. Basically, it has to go, style has to evolve in a very smooth way. And this is what the machine discovered. So the machine getting sophisticated in understanding the formal element of art at least, but it's still missing, of course, the deeper understanding when it comes to the human level understanding of semantics of art.
And so, speaking of human level of understanding, I worked for many years on something called the Art Genome Project, which is a purely manual classification of art. How does the state of image recognition and the kind of things we do with machines today compare to those manual metadata projects? Where do you think they fit together?
Yes, that's a very important point. So going back to the Barnes problem when they wanted to have this AI, definitely the Genome Project used a lot of manual annotation by a human artist, a human art historian expert to annotate a lot of attributes about art. And that's interesting, but I believe that an image worth a thousand words, and it's very hard to really get the information out of the art and annotate manually using that. That's why we built what we call the Art API, an AI engine that are really designed and built from the ground up for art, that has the ability to understand formal elements like basically style, genre, subject matter, composition, space, light, color, and all element and principle of art, try to quantify these from art. And based on that, it can do visual search very efficiently and in an artistic way, and also can recognize all these elements and quantify them. So basically, give it an artwork like that. It can tell you it's a pop art, it's a portrait, it's Warhol, and quantify the space, it's shallow, the contour are sharp, the light is diffused, the lines are curvy, and based on that, it can really search larger collection and find these things. And this is basically how the Barnes use it. So if you now go to the Barnes and go to the collection, this is the only museum in the world now that have AI and computer vision in the background, allowing their users to navigate the collection and discover things without any annotation. So here there is no human annotation involved at all just basically the AI is driving the stylistic relation between the art that you look at and allow you to discover things, make connection between artists, make connection between pieces at different ages, and navigate.
So you're in a way you're saying that the machine here performs better than a human?
It can work. Human doesn't have the capacity to deal with massive amount of data. Mm-hmm. It's a lot of work for human to annotate lots of attributes for artworks. Besides, also human will tend to be inconsistent. Probably if you have been doing that, so you see that different people will have different opinions about quantifying certain attributes about art. Mm-hmm. And I know, for example, the Met Museum has a project a year ago where they have crowdsourcing annotation of artworks in their collection. And to their surprise, I told them that it won't work. Basically, everybody annotated art differently. Because it's very hard to come up with this. Besides, language is always a higher level intelligent than looking at the images. So when you move from an image to describe the user language, that's really a complicated thing. While images are also information that you can really capture without the need to go to language as a proxy.
Mm-hmm. That's very interesting. If we take this idea further and believe that machines can be more effective when a lot of data is involved, what are other places where we can apply machines and specifically machine learning and maybe AI in the art industry? What are other topics? What are the problems that you think machines can solve?
Yes. So let me move forward here to answer this question. Yes, so machines are good at two things. At the macro level, being able to look at massive amount of data, like in that figure on the left, this is that's showing actually 80,000 artworks in the Western art history in one graph, and color-coded by time. And again, that arrangement is done automatically by the machine. We never give the machine the time label, but the machine really discovered that. Mm-hmm. So the machine can give us these insights about art history that we cannot really tell as human because we don't have this ability to mass that large amount of data. In the micro level, the machine can do very good job at looking at the details of the stroke that led to Jason talk earlier about basically forged art and how to discover that. So here we developed an algorithm that look at the stroke level in drawing, and we show that there's a signal in the strokes, in individual strokes, that you can tell who is the artist. You can tell whether it's a Picasso or Matisse or a Schiele drawing just from a single stroke. There's a signal there because it's bending on the pressure on the paper that you can capture. So, for example, we use this to detect forgery. One of these art are real Picasso, and one of them is forged art. That's an easy example. I guess you can tell who is it. But the algorithm will analyze this stroke by stroke and give it a red or green signal. So green is most likely Picasso, red is most likely fake. Here's another harder example. One of them is Matisse, and one of them is fake. Can you tell which one is the real Matisse?
I'm going to pick left just because it's different from the previous slide.
That's wrong. The left one is the fake one. Yeah, good fake, because actually you commission artists to do good fakes, but the algorithm could tell that. Another example, one of them Matisse, one is fake.
Do I get to pick again?
Yes.
Sure, the one on the right.
I guess you are right this time.
Yes. So if I'm right, maybe we should just employ humans to do this job. Do we really need machines?
That's very important.
I can be trained easily to recognize fake materials.
It's very hard, actually, not easy at all. And that's exactly what machine is good at, because there are lots of strokes in here, right? And and forger will deceive you because they will copy the composition and the subject matter very well, but it's impossible to get the stroke. And the stroke level, it's something very hard for a human to really mass the statistics that's needed for doing that.
But if I have the machine available to me, I can also train another machine to just make fakes the same way. Aren't we just creating a new problem with a technology solution?
That's a good point. But actually, if you create a fake, you have other problem, because I mean, when it comes to authentication, there are a lot of technologies that has to be employed. There are pigment analysis, there are canvas analysis, there are all these things. What we're adding here is a complementary solution to that, which is how to look stylistically at the art and give the expert a way to quantify that stylistic element, so that he can make a decision. But if you can fake that art, you cannot actually print it on the right material and with the right pigment. So other techniques will
yeah. So a combination of technology to solve these problems. Do you think that what part in all of this will remain human if we go maybe 50 or maybe 100 or 200 years forward?
Yeah, a lot of things. These are just tools. Are just tools that makes our life easier. It helps us mass a large amount of data, look at details, quantify things, and move forward faster. That's not going to replace humans, just going to help humans.
Give us a prediction on image recognition and vision as a science, and where do you think what do you think it will be capable of in our lifetime? How will it apply? What will be possible with AI on top of the data?
That's a hard question. Vision is very hard because it's deceivingly easy. More than 20 years ago, we have the first time a computer beat the world champion in chess. And we always think of chess as something that only intelligent people would do. However, vision is much harder because till that time, till like a few years ago, vision systems was just like as good as a 2-year-old. And maybe now, I mean, with most vision system, well-trained still will do errors as a toddler or a kid would do learning how to see. So it's a long way. It's a deceivingly easy problem. But in domain-specific things, if you train it on one problem, like authentication in that case here, or driving a car, or it can do a great job because you have enough training data, you can really achieve a lot. But we are very far away from building a vision system that's generic enough that can do all the tasks that we do as human and connect things also. Like we humans are very good at connect different sources of information, looking at our knowledge and using that to do inference about what's happening around us. But while vision systems just do one thing at a time that are trained to do, so it's not good at really looking at the big picture.
Great. I only have one last question. what year will it be that I leave this yearly conference at Christie's and take a self-driving cab home?
I don't know. I was reading an article a couple of days ago that the biggest problem with autonomous car is that there's going to be human driver in the roads. That's the problem. I mean, imagine that world that we have all autonomous cars only. That can happen actually today if the roads are only autonomous cars, because it's going to be easier to communicate with each other. But having humans on the road as well to complicate the problems, because there are a lot of unpredictable things happening. But I'm looking forward for that. I mean, I will be the first person to buy an autonomous car if it appears tomorrow and I can afford it.
But you still have to pick a year.
It's very hard to predict because the technology is there now. It's available now. It's driving in the streets now for testing. But there are a lot of legal issues that has to be resolved. There are a lot of interaction issues and psychological issues. So it's not about the technology as much as how the society accepts it.
It's a real scientific answer to my question. For what it's worth, I predict somewhere around 2025. That's my unscientific